Okay, moving on our review, let's look at making some proofs for identities. So in 14, A, B, and C, I've got some identities that we need to prove. Now, with that said, remember identity is an equation that's true no matter what we plug into the variable. So we should be able to show both sides are identical. Right? We could graph the two sides and show they overlap. That'd be one way to prove it graphically. Or we can just prove it by hand, right? By simplifying. What I do is usually pick the more complex side, right, of my identity and try to obtain the other side. So work on simplifying it. Or you can work on both sides at the same time until they match up. But we've got to make that proof happen. So when I'm looking at 14a, I'm looking at the right-hand side. So let's work on it. So as we simplify that, my first step is go ahead and rewrite cotan and tan using my quotient identities. All right, so we can write a note over here on the side. Apply quotient identities. So this is equal to 2 divided by, well, cotan is the same thing as cosine x divided by sine x. And we know that tangent, applying the quotient identity, is defined as sine over cosine. All right. So now we've got everything in terms of sine and cosine. And what I want to do now I want to clear the fractions. All right, so that's my next step. All right, so remember our LCD, we can multiply by that. So our least common denominator is the product of all the different denominators, different factors. If any are repeated, we use the one that occurs a greatest number of times. But sine x times cosine x would identify as our LCD. So I want to times, right, both sides by that. So again, multiply by LCD. All right, so let's go ahead and write that down. All right, if we multiply by a common denominator, we'll be able to divide out those denominator factors. So we're going to times by sine x, cosine x, with the numerator and the denominator. So as we do that, as we simplify that down, our numerator now reads 2, right, if you want, we'll keep it in the same color, 2 sine x cosine x, all right, divided by, now in the denominator, let's go ahead and distribute. So we're going to multiply that through to both. Now we multiply cosine over sine x times sine x cosine x. The signs divide out, all right, and that will leave me with a what? That will leave me with a cosine x times sine x. Times cosine x. All right, sine x's divide out, right? They cross out here, so we distribute. So it leaves you with cosine times cosine. And then as you distribute to the next term, and we can go ahead and take that off, we will multiply sine x of cosine x times sine x cosine x. The cosines divide out, and that'll leave me with sine times sine. So let's go ahead and write that down. What's left in our second term? We got a sine x times a sine x in the second term. All right, so it's clearing out the fraction, simplifying nicely. And let's now write down the product that's remaining. So we have in the numerator 2 sine x cosine x divided by cosine times cosine, which is cosine squared, minus sine times sine, which is sine squared, x. Well, now we got two identities, right? So we got double angle identities. So let's make that note. Apply double angle identities. So we know right here, for example, this is the double angle identity for sine. This is equal to the sine of 2x. And the denominator, hopefully you recognize, is a double angle for cosine. That's cosine of 2x. So as we simplify this fraction down, the numerator is now sine of 2x divided by the denominator, which is cosine of 2x, which from the quotient identity, right, defines the tangent of 2x, right? Apply quotient identity. Write that over here on the side, our steps. And now we have our proof, right? So there's the proof right here. So tan 2x and tan 2x. Left and right side are identical. So you can see I picked a more complex side, the right side of this identity, and I simplified it down, doing a little bit of algebra, right? Getting rid of fractions. Those are one of our steps, but mainly identities. Applying the quotient identities, right? Tangent sine over cosine, cotangent's cosine over sine, right? Clearing out the fractions, recognizing the double angle identities it produced, right? And then the quotient identity again at the end finished out our proof. All right, let's go do the same thing in 14b so we can make a proof for this one. Now in 14b, we're looking at the right-hand side, right, and the left-hand side. Which side do you want to work on? Well, to me, the more complex side is the left-hand side. So I'm going to work on this side first, right? So my goal is to match it up with the right-hand side. All right, and as we do that, all right, let's go ahead and apply our identities. So we're going to apply the difference identity for sine. All right, we can make that note. Apply difference identity for sine. All right, so remember, what does it equal? So difference identity for sine is sine of u times the cosine of v minus the cosine of u times the sine of v. All right, so there's the difference identity for sine, right? Sine of u minus v equals, so again, sine u cosine v minus cosine u sine v. And all that's divided by sine u times cosine of u. All right, now what I'm going to do is I'm going to separate it. So we've got a fraction. Let's go ahead and separate it into two fractions. We've got two terms in the numerator. So let's go ahead and divide both terms by the denominator. All right, so we'll break this up, separate it. All right, so we make that note, and I'm going to put a little note here on the side. And now look for common factors. So for example, we have a sine u divided by sine u. So they divide out. Over here we have a common factor of cosine u dividing out. All right, so dividing out the common factors. And now what are we left with? So we're left with cosine v divided by what? Cosine of u. Be careful with that. That's a u here. So we're left with cosine of u here in the denominator minus, and here we're left with a sine of v in the numerator divided by the sine of u. All right, so keep in mind what we're trying to get to. We want to match up the right-hand side, which is secant u cosine v minus cosecant u sine v, which I can see. So this is equal to, we can separate. So this is equal to 1 over cosine u times cosine v minus 1 over the sine of u times sine of v. And here are my reciprocal identities. All right? So let's apply the reciprocal identities. All right? So again, let's write that note here. All right, so that equals what? Secant of u, right? Secant is 1 over cosine times cosine v minus 1 over sine is definition for cosecant of u times sine v. And we've made our proof. Now we've got exactly what we want. So here it is in the end, what we have on the other side of the identity. We've matched it up. So we've made a proof, right, for this identity. So it matches up. Left side and right side identical. And that's our work. So applying the reciprocal identities was the key step there. So recognizing that, right? Be able to use those identities. All right, let's move on. We got one more. Let's look at our last one. Let's take this third example. If I'm looking at it, let's work on more complex side to me. Looks like the left-hand side, right, in this next identity. So I want to work on this one. Let's see if we can match it up to the right-hand side. So right now, first thing I'm going to do, let's apply sum of cubes. All right, so we're going to factor. So let's go ahead and write that note here on the side. We need to review. We can write that over here. So remember, what is the sum of cubes factor? A cubed plus b cubed equals a plus b times a squared minus ab plus b squared. All right, so that's our sum of cubes, right, factor. So we're going to apply that. All right, so let's go ahead and do that. So let's use that property here. So this is equal to, all right, we got cosine of beta. Cosine of beta is being cubed, and sine of beta is being cubed. So there's my a and my b, times a squared, so cosine squared beta, minus the product of those, which is cosine beta, sine beta, so minus ab, plus the square of b, so plus square of sine squared beta, all divided by cosine of beta plus the sine of beta. All right, and now what I'll do is separate or look for common factors, I should say. So we have a factorization in the numerator, and what do we see common in the numerator and denominator of this fraction? We have a cosine beta plus sine beta. So this fraction is simplifying nicely. So now we've got what? We've got cosine squared beta plus, or I should say minus, cosine beta sine beta plus sine squared beta. And then I've got the Pythagorean identity to apply. So let's say, what do I see here? Cosine squared plus sine squared. Right, we know that equals 1. So our fundamental identity, the Pythagorean identity. So in the end, as we simplify down this left-hand side, the more complex side of our identity, we end up with 1 minus cosine beta sine beta. Now, I don't have a proof, but I have my left side in simplest form. So now, let's go to the right side. So that'll be my next step. All right? My next work on right side. So I want to simplify the right-hand side. All right, so let's go focus on it. So where's the right-hand side? If you want, we put in a different color, but here's the right-hand side. 2 minus sine 2 beta equal 2. Well, let's apply the identity. So if you want, we got 2 minus, well, sine of 2 beta, that's equal to 2 sine beta cosine beta, all divided by 2. So double angle identity. Write that in here. Double angle identity. And then we can break that up. So let's go ahead and break it up into 2 fractions. So we'll separate. That's 2 over 2 minus 2 sine beta cosine beta over 2, which is equal to what? So we reduce. We get 1 minus sine beta cosine beta, which is the same thing as 1 minus, doesn't matter the order, it's commutative. 1 minus cosine beta sine beta. So there it is. We've matched up. So we've got our left side, we've got our right side identical. All right, there's our proof. All right, so made our proof happen. So we've proven this identity. So apply double angle identity, separate it into 2 fractions, right? And then we had it, a couple steps. So that's proofs, a little review of proven identities, showing both sides identical. Moving on, let's do some properties of inverses. Let's review our inverse properties. It says find the exact value in radians. It says 15 A, B, C, D. It says 15A, sine inverse of square root of 3 over 2. Well, we want to find sine inverse square root of 2. Our question is this, right? Again, what does this equal? Right? Sine, right, of what number equals the square root of 2? Right, so that's what we're looking for. We want to find that number. Now, with that said, right, we'll make that, we'll give it a variable, call that y. Right, so we'll put y here. Sine of what number y equals square root of 2. Remember the range. Range of sine inverse of x is equal to negative pi over 2 to pi over 2. All right, so again, y must be in that range. So again, this is what we're looking for, between negative pi over 2 and pi over 2. Now remember, sine is evaluated with what? Y coordinate. So we can use our unit circle approach. We don't need a calculator on this one. Hopefully you recognize as one of our special angles. All right, when is our y coordinate? Square root of 2 between negative pi over 2 and pi over 2. Well, that occurs at what? Pi over 3. So if you were looking at the unit circle approach, I'll write that down. At pi over 3, you have an ordered pair of 1/2 square root of 3/2. There's that y coordinate. So that implies the sine of pi over 3 is equal to square root of 2, right? The y coordinate. All right, so there's our answer. So that implies what? Sine inverse. So there it is. So there's the y coordinate, pi over 3. So that implies sine inverse of square root of 3 over 2 is equal to pi over 3 radians. All right. So that's inverses. Let's go ahead and do example B. Let's see if we can figure that one out. Again, we shouldn't need a calculator. All these ask for exact value. This one wants to know what tangent is equal to. So let's find it. So it equals what? What number y? So again, tangent of what number y equals 1. So with that said, remember with our unit circle approach, y coordinate out of x coordinate. And the range, we can write it over here. The range is between what? Negative pi over 2 and pi over 2. So we studied our range for sine inverse, tan inverse, and what? cosine inverse. But that's our range on that one. Now, as we look at that, when would you have a tangent value 1 in that range? Well, look at pi over 4. All right, so again, using the unit circle if you need to, pi over 4, we have an ordered pair of square root of 2. Square root of 2. There's your x and your y coordinate, so that implies the tangent of pi over 4 is equal to square root of 2 divided by square root of 2, which is equal to 1. Right? So that implies tan inverse of 1 equals pi over 4 radians. Right? Which, again, is in the range of that. Moving on, we got cosecant inverse, and we have secant inverse to look at. Right? So be careful on these. Do want to refer back to, if you need to, refer back to your properties, right, for sine inverse and cosine inverse, for that matter. But if you wanted to, we could rewrite cosecant. All right, so let's do that. We know cosecant, our inverse square root of 2. All right, that's the same thing as saying this is equal to sine inverse of 1 over square root of 2. All right? And as we rationalize that, let's go ahead and rationalize. All right, we would have sine inverse of square root of 2 over 2. All right, so if you were looking at your sine properties, right, and range is between negative pi over 2 and pi over 2, all right, you're looking at, again, what's y coordinate? So sine, right, of what number? Going to give you square root over 2. And again, range between negative pi over 2 and pi over 2. And if you need to get out your unit circle, you can. So we'll do the unit circle. All right, range of 10 between negative pi over 2 and pi over 2. Well, pi over 4, we have that ordered pair of square root over 2, square root over 2. So sine of pi over 4 is equal to square root over 2, y coordinate, right, which is what we're looking for. So that implies, right, sine inverse of 1 over square root of 2, or square root over 2, is equal to pi over 4, which implies cosecant inverse of square root of 2 equal pi over 4. All right, so again, we use the unit circle, right, approach, use sine to define that. All right, let's move on. Let's go to example D. All right. And just want to refer back to, real quick, see if I have it up here. We don't have our properties, but we could refer back to them. We'll look at that later. But let's go to example D. All right. In D, we got secant inverse of negative 2. All right. So with that said, what are we looking at with secant inverse negative 2? Let's redefine it using cosine. All right. We know all about cosine. All right. So we could use that, all right, to help us. So we can use our reciprocal properties, all right, to define that. All right, so I'm going to go ahead and do that. So secant inverse negative 2, well, that's equal to cosine inverse using reciprocals of 1 over negative 2. So that's cosine inverse of negative 1/2. So looking at cosine, got to be careful. So with that said, we're going to look at the range of cosine inverse. All right. And what is the range of cosine inverse? We can write it down before we do it. But again, our question is this. Cosine of what number is going to equal negative 1/2? And we know we're looking at x coordinate, right? Sine is y coordinate, cosine is x coordinate, tangent is y over x. So if you need to, let's go refer back to our unit circle. All right. And we know we're talking about in cosine, I'm going to write this down. Our range on cosine is from 0 to pi. So be careful with that. So in the unit circle between 0 and pi, when would you have a x-coordinate of negative 1/2? It'd be over at your pi over 3 mark in quad 2. That'd be pi minus pi over 3, which is 2 pi over 3. At 2 pi over 3, you have an ordered pair that reads negative 1/2 square 3/2. It's a reflection of pi over 3 across the y-axis. Same coordinates, except now the x-coordinate negative was in quad 2. But that's the 60-degree mark, or pi over 3 mark, quad 2. And there it is. There's that x-coordinate we're looking for. So that implies the cosine of 2 pi over 3 equals negative 1/2. Well, there's our cosine inverse. So cosine inverse of negative 1/2 is equal to 2 pi over 3, which implies secant inverse of negative 2 equal 2 pi over 3. All right? So again, rewriting it with cosine. All right, let's look at some composition properties. So looking at our next set of problems. And I do want to show you, again, all of these you can look at in your calculator. If you need to, your TI will handle these. We didn't check any of these, but we could have. And if you wanted to use your calculator, it might help you to put it in degree mode. Right, and you can get degree measurements back. Just to show you, for example, you go back to 15A. So go to your calculator real quick. We'll pull that up. Hit your mode key. Go down here to degrees and turn that on. And if you go back to first example, we had sine inverse of what? Square root of 3 over 2. Let's type that in. All right. As we type that in, right, hit your enter button. You get 6 degrees. There's pi over 3. Right? I'm in degree mode. So pi over 3 is equivalent to 6 degrees. Right, there's our answer for 15A. So we can let our calculator do it, but these are ones we should know because they're all dealing with special angles. Remember, anytime they ask for the exact, we're not going to have to use a calculator to get it. They should be quick and easy using these special angle measurements that we've been looking at all semester. Moving on, let's go to number 16. We got some composition properties, looking at inverses. We got 3 of them here, 16, A, B, and C. 16A, actually one of our shortcuts, sine inverse of sine of pi over 7. Well, that's going to equal pi over 7. So here's a property for inverse functions. And we can write it over here on the side. Sine inverse of sine of x will always equal x. Right? As long as x is in the, what? Range. So as long as x in the range of sine inverse. So as long as it's between negative pi over 2 and pi over 2, you're good. All right, so with this problem here, that equals pi over 7. So we can use our shortcut. All right, look at example B. Now example B, I've got cosine of cosine inverse of 0.2. All right, 2/10. Well, again, same property. And we'll look at the property here beneath it. We know the cosine of cosine inverse of x will always equal x as long as x is in the domain of cosine. Domain of cosine we know is what? Cosine inverse. We know the domain of cosine inverse is negative 1 to 1. So long as between negative 1 and 1, we're okay. So again, there's our domain of cosine inverse and of sine inverse. Between negative 1 and 1, which it is, 0.2 is in there. So long as x is in domain of cosine inverse, this is going to equal 0.2. All right, now you look at the last one, no shortcut on this one. All right, we got sine inverse of cosine. So these are different functions. So we're going to have to simplify inside out. So this is equal to, well, let's go ahead and find out. What is cosine of pi? So we'll go here to the side. So cosine of pi is equal to what? Well, at pi, let's use the unit circle. On the unit circle, we know pi gives us an ordered pair of negative 1, 0. So there's the x-coordinate and the y-coordinate. So cosine of pi equal -1, right? Equals the x-coordinate. So as we go back to our problem, this is equal to sine inverse of -1. And what's sine inverse of -1? What does that equal? So our question is this. So we're asking ourselves, right? Sine of what number is equal to -1? So again, we want a y-coordinate to be -1, and it needs to be in the range. So remember, the range on the sine inverse function is -pi/2 to pi/2. So that means we're going to have a value of -pi/2. So at -pi/2, we have the ordered pair of 0, -1. There's that y-coordinate. So that implies the sine of -pi/2 equal -1. All right, so here's our answer. So what does it equal? It equals -1. Equals -pi/2. So simplified down, we get -pi divided by 2. All right, so again, that's simplifying down using our properties. And you can check it if you wanted to on your TI. Again, you want to go to your calculator and look at that one, you can. We already got it in degree mode, so let's type that one in. So we hit, what we have, second sine inverse. Clear out our last problem, second sine. Cosine of pi, now we have in degrees, we'll put 180. And we get -90 at -pi/2. So again, it's reviewing your composition properties. All right, so it's looking at last three problems, solving our trig equations, 17, 18, and 19. Solving our trig equation, we want to find the values of x to satisfy this statement. Now it says in our directions, find all solutions between 0 and 2 pi. So restrictions on solution set. All right, so let's make that note here before we begin. Now, as I'm solving these, a lot of algebra involved. When I see this example in problem number 17, there's my x term. I only have one x term, the squared term. Well, with that said, we could just isolate and use principal roots to solve it. So let's go ahead and isolate that term. So get it by itself. All right. So as we do that, we'll go ahead and add the 1 over to both sides. That'd be my first step. So as we add 1 over to both sides, that implies 4 sine squared x equal 1. And then we divide out our 4 on both sides to get the x squared term isolated. So I'm treating it just like I would if it was x squared instead of sine squared. I'm getting that term by itself so I can use roots. So now I'm ready. Principal roots. We know we have a square and we want to get to x. We're going to take the square root to both sides. Since it's an even root, be positive or negative. Don't forget that. We know the square root of sine squared x is sine x, what we're looking for, plus or minus the square root of 1 over the square root of 4, which, what is that? That's sine of x equal to plus or minus 1/2. And now we can solve that. Now I don't need a calculator. Yeah, I could say, well, sine inverse of 1/2 equal what? Now we're positive and negative. This is a special angle. Let's think about sine. All right. Sine's evaluated by y-coordinate. So if you need to, get your unit circle out. So on the unit circle, let's go ahead and envision that. When do we have y-coordinates of 1/2 or -1/2? Well, in quad 1, we have a y-coordinate 1/2 at pi/6 radians. Right, we have the ordered pair square root of 2, 1/2. There's that y-coordinate. So that implies the sine of pi/6 equal 1/2. So pi/6 is the solution. So that implies x equal pi/6, which is between 0 and 2 pi. Remember, our restrictions greater than or equal 0, less than 2 pi. All right, when else we're going to have a positive 1/2 for y-coordinate? Go to quad 2, between 0 and 2 pi. What's our pi/6 mark? Pi minus pi/6 is 5 pi/6. So if you need your unit circle out, you can. At 5 pi over 6, we have negative square root of 3 over 2, 1/2. So that implies the sine of 5 pi over 6 also equals 1/2. So 5 pi over 6 is also a solution to this equation. And then as you go to quad 3, at 7 pi over 6, we have the ordered pair of negative square root of 3 over 2, negative 1/2. So quad 3 point, and again, now our y-coordinate, negative 1/2. And remember, we can be positive or negative. So sine of 7 pi over 6 equal negative 1/2. So that's a solution. So we got to add that to our solution set. And then to finish it out, between 0 and 2 pi, I go to quad 4, our pi over 6 mark, which is what? 11 pi over 6? 12 pi over 6 minus pi over 6, 2 pi minus pi over 6. At 11 pi over 6, we have an ordered pair of what? Square root of 3 over 2, negative 1/2. There's that y-coordinate. So the sine of 11 pi over 6 equal negative 1/2. So we have our last solution, 11 pi divided by 6. You could check them. You could graph it, see these intersections. If you're using the zero method, you would see your graph cross through the x-axis at 30 degrees if you're in degree mode, or pi over 6 in radian mode. 5 pi over 6, which is 150 degrees if you're in degree mode. 7 pi over 6, just 210. 11 pi over 6, which is 330. So you could check those two graphically. It was nice to graph it and look at it. But we found our solutions fairly easily. These were, again, working with special angles. Didn't need a calculator to get them. But again, a lot of algebra involved in these problems. All right, let's go to 18. Let's solve x. So again, we're trying to find out what x equals. Well, when I see this problem, my first step is I need to factor. Step 1. All right, I've got a greatest common factor of tangent showing up. I got two terms and tangents in both. All right, so that implies we have the tan of x. As we factor that out, we're left with 2 cosine x plus square root of 3. All right, and then we can apply our zero factor proposition. So apply zero factor property. So once we have a factorization, right, we can set each factor equals 0. So we know if this product is going to equal 0, one of these factors is going to have to be 0. So that implies the tangent of x, one of our factors, would need to equal 0, or 2 cosine x plus square root of 3 would need to equal 0. And we can go ahead and work on solving this one. So when is tangent of x equal to 0? So you think about your unit circle. Right. We need our y-coordinate divided by our x-coordinate to be 0. So again, on the unit circle, and we can go down here. Between 0 and 2 pi, when do we have a tangent value 0? That means our y-coordinate would need to be 0, right? Because 0 divided by anything is 0, except the number 0. But if we look at, for example, at 0, right, the 0 radians, our ordered pair is 1, 0. There's x, there's y. So that implies what? The tangent of 0 radians or 0 degrees is equal to 0 divided by 1, which is equal to 0. So that implies x equals 0. We also have, go to pi. At pi, we have the ordered pair of negative 1, 0. All right, so there's our x-coordinate, there's our y-coordinate. So if I said what's the tangent of pi, you would have 0 divided by negative 1, which is 0. So that implies pi is a solution. So there's two solutions. So again, from the unit circle, right, we've got these two solutions. Now we also have the other factor. So we still got a little work to do on it. So we're trying to solve x. So we need to isolate. Get x by itself. So next step's to subtract square root of 3 over. As we do that, we get 2 cosine x equal to negative square root of 3. And then divide out our 2 on both sides. And we'll have the x term where we want it now, isolated. So that implies cosine x equal negative square root of 2. And remember, with cosine, and we should recognize this one, we need a x coordinate. Cosine is divided by x coordinate. So again, on the unit circle, right over here on the side, when do we have an x coordinate that's negative square root of 3 over 2 between 0 and 2 pi? Well, when we're looking at our pi over 6 mark in quad 2. So if I said at 5 pi over 6, what's the ordered pair at 5 pi over 6? Negative square root of 3 over 2, 1/2. There's that x coordinate. So that implies the cosine of 5 pi over 6 is equal to negative square root of 2. So there's a solution. So that implies x equal 5 pi over 6. Now we also have at 7 pi over 6. Write it down. At 7 pi over 6, we have negative square root of 2. Negative 1/2. So that implies the cosine of 7 pi divided by 6 is equal to negative square root of 2. Again, there's that x coordinate, right, we need. So there's another solution. So 7 pi over 6 is also a solution to include. So in the end, we have 4 solutions. So altogether, our solution set, we can put it down here at the bottom. X is equal to, we'll put them in order, 0, 5 pi over 6, pi, and 7 pi over 6. Now we don't include 2 pi. You say, what about 2 pi? That is ordered pair of 1, 0. It means the tangent value would be 0 there. But remember, our restrictions had to be less than 2 pi, not equal to. So there's the solution set on 18. So we take those two together. So 4 solutions coming together. Now our last one, problem 19. I like 19. 19 involves identity. All right, we got double angle identity. That should be our first step. Apply double angle identity. We want everything written in terms of x so we can solve for x. All right, so that implies, let's go ahead and do that. So we have sine of x times, well, sine of 2x is 2 sine x cosine x plus sine of 2x, which is 2 sine x cosine x, all equal to 0. Well, what's our next step? So we're looking at that. Well, we go ahead and factor that out, right? Our common factor. So sine of 2x, let's go ahead and bring out that GCF. So if we do that, let's go ahead and factor next. That's our second step. We'll factor out that common factor of sine 2x, which will be broken down in terms of x, which is what we want to do, right? We want to get in terms of x so we can solve for x. So I want to get rid of the double angle. So we bring out that GCF. So we bring out 2 sine x cosine x. We're left with, in our first term, we're left with a sine x. And we're left with 1 in the second term. We're bringing out all of it. And then we're ready to apply the zero factor property, right? So at this point, now we do have a coefficient of 2, and then we can divide that 2 out. But this is where we go to our zero factor property. So any factor of x, we're going to set it equal to x. So sine x, cosine x, sine x plus 1. So that implies sine x can equal 0, or cosine of x can equal 0, or sine of x plus 1 can equal 0. And we can easily solve these. When does sine hold a value of 0? So we're asking ourselves, when is our y coordinate 0? Here we got cosine of x equals 0. We're going to be asking ourselves when our x coordinate is 0, right? Cosine's x coordinate. And we got to solve the last one. We got a little bit of work. But let's go ahead and write these solutions. So on the unit circle, right, when do we have a y coordinate of 0? So we have a y coordinate of 0 at 0. At 0, we have the ordered pair 1, 0. So that implies the sine of 0 is 0. There's a solution. That implies x equals 0. We also have at pi, we have the ordered pair of negative 1, 0. So that implies the sine of pi is equal to 0. So that means pi is a solution. And then we go to cosine. So let's go ahead and write down these solutions. So from the unit circle, when is our x-coordinate 0? X-coordinate 0 at pi over 2. Pi over 2, we have an ordered pair of 0, 1. So that implies the sine of pi over 2 is equal to 0. So pi over 2 is a solution. We also know at 3 pi over 2, we have an ordered pair of 0, negative 1. So it has an x-coordinate of 0. So that implies the sine of 3 pi over 2 is equal to 0. So there's a solution. So we got two solutions for that one. Now this one, we still got to solve for x. Go ahead and subtract that 1 over. We got a little bit of work. So here we have the sine of x equaling negative 1. And now our question is, when is our y-coordinate? Negative 1. So again, on the unit circle, right? All right, what do we have? When do we have a y-coordinate of negative 1? On the unit circle, we have a y-coordinate negative 1 at 3 pi over 2. Right? We have the ordered pair of 0, negative 1. So that implies the sine of 3 pi over 2 equal negative 1. So x equal 3 pi over 2. So altogether, our solution set. So now we can write it in here. So for this equation, we put all these answers together. We have 0, we have pi over 2, we have pi, and we have 3 pi over 2 for our answers. So writing those in here, and I'm putting them in order. So altogether, we got, what, 4 solutions? And there are those 4. All right? So solving trig equations. Really not a lot going on with it. That problem, we applied one identity. We applied the double angle identity for sine. Did a little factoring, zero factor property, but algebra review and solving equations on these. But those are some good examples of solving some trig equations. So hopefully these problems will help you in preparing for your unit test here for Chapter 7. All right, so that's it for our review.